Shall I check? Let's begin. Do I have all the quizzes? So, last time.
Oh, fuck,
So last time, it seems like forever ago. We did a lot of things. We derived a lot of rules, and let's just, before we get into the examples that we left to do, let's remind ourselves of the rules. So, define for me the derivative. What is that? Yeah.
Well, as h approaches 0, f of x plus h minus sec of x over h.
Right? That's a limit. It is called the derivative. It helps us to find the slope of the tangent line to a function f of x at the point x, or that is the slope of the function, or we call this the rate of change of f, or we call this the instantaneous rate of change of f, or we say this is how fast f is changing with respect to y. And by using that, you can derive a bunch of things like the power rule. What's the power rule? What's the power rule say? Yeah.
X to the n, dx
The derivative of x to the n.
equals to n x n.
And we also derive the product rule. What does that say? Come again? What's going to be, what's the left side of the equation? That's not complete. Yeah?
ddx of fg
ddx of f times g is
f prime times g
times g plus
f plus g.
Right, differentiate one at a time. Knowing the left side of the rule is very important. Don't just know the right side. You want to know the entire rule. Okay. So every derivative rule that we have for like all these guys, it starts with a ddx of something. You want to know the derivative of a certain form is another form. You want to memorize it like that. What about the quotient rule? How does that look? Yeah.
ddx
F over G
equals f prime g minus fg prime over g squared.
chain rule. What does that look like? Yeah.
The derivative of f of g
F of G, which means you're plugging one function into the other one.
is going to equal the derivative of the outside function. So derivative f
Right? The inside function stays in the first place, and then
times the derivative of g.
you multiply by G prime, which note that you may have to put in parentheses if it has several terms, because it would have to multiply out. So these are the big rules. They work very, well, especially, except for this one, they work very generally, but we also needed to know how to differentiate particular functions. One particular function we looked at was the exponential function. Let's look at e to the u. What is the derivative with respect to x of e to the u? Yeah.
U prime e.
U prime e to the u. You find the derivative of the power, you multiply by the original function. What was the derivative with respect to x of ln of u? Yeah.
Oh, u prime over u.
U prime over u. If I asked you what was the derivative of the sine of x? Was the cosine of x? The derivative of the cosine of x minus sine of x. The derivative of the tangent function. Huh? Secant squared. What if I ask you, what is the derivative of a general logarithm, log to the base a of x? 1 over x line. What is... Oh, here's a fun one, the quiz. Let's look at one of these guys. What's the derivative of this one? Yeah? 0. How do you know so quick? That's 1, yeah. And that's a constant. And we had a rule, the derivative of any constant is, well, 0. So you didn't even have to really do it. You could look at that and know what the answer is. If you remember the rules, for example. This is why it's important to remember the rules. Every now and then you'll see a problem. It would look very complicated, it would look very difficult, but one thing that is going to be true for a while in mathematics, up to Calc 3, differential equations, vector calculus, is that difficult problems are really just combinations of little smaller ones. If you don't understand something, there's a very basic reason why you don't understand it. Go back to the rules. So we can, the rules here, like the quotient rule, the chain rule, and the power rule, and the product rule, they tell us how, if we build up a complicated function, how do we actually still find its derivative? By just considering the little pieces that it's made out of. So that's why those rules are very important. It's why you need to remember them exactly. So yeah, we knew the derivative of a bunch of functions, and with those rules I gave you, power rule, product rule, quotient rule, chain rule, all that good stuff, we can find derivatives of more complicated and complicated functions when we add things and put things inside of other things. So that is quite useful. It's something that you need to know. Now, we will be doing some applications of derivatives, but for a while, we're just going to be learning how to compute derivatives in various contexts, how we actually find a derivative. That being said, let's jump into the examples that we put on the board last time. So last time we did some examples interspersed all over the place, but let's actually just do a battery of examples to make sure that we have the ideas organized in our minds correctly. So we had a bunch, let me write down a few at a time. So was to find the derivative of the sine of x divided by x, the derivative of x plus 1 over x plus 2, the derivative of x squared. Let's start with those. Hey. What do I want to do here? Huh? Quotient rule? Why the quotient rule? Because we see a certain form. We see f divided by g, right? We want to find the derivative of something of that form, and we have an equation that tells us how to do that. Well, it's going to be f prime times g minus f times g prime all over g squared. That's what the answer should look like. So now, f prime cosine times the g, which is just x, minus f, which is just sine of x, times the g prime, which is 1, all over g squared, which is x squared. So, now, you don't have to write down this rule all the time, but that's what you're thinking while you're doing this. So, I mean, at this point, it doesn't really simplify much. I mean, x cosine x minus sine of x all over x squared would be a nice enough form to leave that in. So that's the quotient rule. And again, it's because you know the rule so well, you know that the derivative of something divided by something this is how we can actually do it. Similarly, cx plus 1 over x plus 2, you would think kind of the same thing, right? You just imagine that the top thing is the f, the bottom thing is the g. And so it's the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. So that's going to be x minus x. I would have 2 minus 1. So that's the guy. Now, here's one thing that you're going to notice with the, pretty much all the rules except the chain rule, and maybe even the power rule. Is sometimes just because you can do something doesn't mean that you should. In the sense that this machinery is very powerful and very sophisticated, but there are times when you can go overboard with it. How would you do this example? Now, most people just say, well, there's a division, so we do the quotient rule. I would not do the quotient rule for something like this. Now, can we think of an alternative? Yeah.
Take out the constant.
Take out a constant, how? Where's the constant?
1/2.
There's a 1/2 here, right? Notice that x squared over 2 is actually 1/2 times x squared. We have the constant factor rule. We can just factor out the half and think of this as x squared. And in fact, that's going to be 1/2 times 2x. And in fact, this would eventually simplify to just x, right? Which is easier than the quotient rule. And in fact, this will be the recommendation. I'm going to tell you why this is the recommendation in a bit. But if your denominator is a constant, I would not use the quotient rule. Not that it's wrong to use the quotient rule, you could use the quotient rule, but in my experience, there are mistakes that students will often make when doing the quotient rule in situations where they really don't have to. If the denominator is a constant, do not use the quotient rule. In fact, you don't even have to think about factoring out anything. What you'll notice is that if you factor out the denominator of the top and you differentiate, when you multiply across, you just get the derivative over the old denominator. So what you can do when you see a situation like this is literally just ignore the denominator, just leave it alone and differentiate the top. So if I want to find the derivative of something that looks like f of x, some function, whatever it looks like, divided by a constant, well, the derivative of that is just the derivative of the top, and leave the constant alone. Right? You don't need to go through a quotient rule for that. And see, what commonly happens here, why I would make this recommendation, not only does it make your life a lot simpler, but there is a common mistake that I see when students are in situations like this. So they would see something like, and it's going to seem very silly when I do it on this small example, but when the examples get bigger and things look a little bit more complicated, it's going to be one of those things that sneak under the radar. What they would do is they would take the bottom times the derivative of the top minus the top times the derivative of the bottom. What is the derivative of the bottom? 0 over the bottom squared. Now, that's 2 squared. Now, here's the thing. Students forget this 0 like all the time. I don't know why, it's one of those things when your brain gets anxious and just decides to not do it. What I see very often is for a student to copy the 2 back here. And so now they get something that they shouldn't have. On the other hand, what you'll notice is that you went through this whole thing just to get a term that's obsolete, that you would ignore anyway. It's just not worth it. Then you're going to have to worry about simplifying what remains. So at best, you're writing down extra stuff that you don't have to write down. And at worst, you will forget to put the 0 here, which I see all the time. You wouldn't believe how often I see that. So whenever they're doing this quotient rule, there's this big thing, and they're like, when they come here, for some reason, they always put the constant instead of remembering the root comes with 0. Especially if I put something, especially if I had a denominator that looks like something like x squared over e to the pi or something like that, forget about it. Right? If they see this e to the pi, they're going to think the derivative is e to the pi, because people just think like that. But it's not. The derivative e to the pi is 0. But the thing is, you forget it over there. It happens very commonly. So you'd either get it correct, but having to write extra and having to simplify more, or students often actually make that mistake and forget to put a 0 in the derivative of the second term. So if you have a denominator as a constant, I recommend don't think quotient rule. Just leave the constant alone and differentiate the top. Let's look at the other list of examples. Log to base 2. There's the next 3. Okay. How would you find the derivative of this? Yeah?
First, you do write it.
Right.
V times d over dx. Actually, 3 times x to the half.
No.
X to the negative half.
Negative 1/2. And then use the power rule, right? Minus 3 over 2. X to the minus 3. That is another recommendation. If the numerator is a constant, don't use the quotient rule. For a similar reason. Now, I do see students rewrite things when it's not necessary for them to rewrite it, but this is a situation in which I would definitely recommend rewriting. So if you have the derivative of a constant divided by a function, I would just rewrite this as the constant times that, and then differentiate the f of x to the minus 1, which may require the chain rule, but at the end of the day, it's going to be easier than using the quotient rule, and you're less likely to make a mistake. In this case, we didn't need the chain rule because it was just, we ended up in a situation where we had the power rule, but depending on the function, you might have to use a chain rule because you have to differentiate the outside, multiply the derivative of the inside. So the quotient rule, powerful rule, but there are times when it's really just overkill and students end up making mistakes because of it. So if the numerator or denominator is a constant, don't use the quotient rule. If the denominator is a constant, you literally just ignore it, differentiate the top. If the numerator is a constant, bring up the bottom to the -1 power and then use the chain rule. So the chain rule is one of those rules that you can't really do overkill. Because the worst case scenario, if you use the chain rule when you don't have to, you multiply by 1. That's literally all that's going to happen. right? So I mean, if you look at, no such concern with the chain rule. So sometimes students, the first time they learn the chain rule, it looks very complicated and sophisticated to them, and they always worry, when should I use the chain rule? You can always use the chain rule. Like that, always. Just use it all the time. Like, you'll never get into a bad situation. Like, let's say you have the derivative of x squared. Yeah, we know that's the power rule, but what if someone imagined it like the chain rule? Oh, it's a function squared. What's going to happen? When you differentiate the outside, leave the inside alone, you multiply by the derivative of the inside, which is it's 1. It's not, right? That you're not going to mess up with the chain rule, right? There are times when you can literally always use the chain rule. It's not going to make a difference in your life. There are times when, though, when you're using the quotient rule and the product rule, that you can kind of use it when you don't need to and just make things more complicated than they have to be. And so if one of the factors is a constant, I wouldn't use the quotient or the chain rule, or the product rule. So similarly, if I have a product of functions and one is a constant, you use the constant factor. You can factor that constant out. You don't need a product rule for that. So those are just some recommendations here. You can use the chain rule all the time you want, even when you don't have to. Worst case scenario, you multiply by 1. But the other ones, just be a little bit more thoughtful when using them. So that would be the derivative of this. What about how do we do that one? Yeah.
So it's e to u, right?
Right, yeah. So this looks like e to the u. So here's where you have some function that's not just x, and we know the rule that says we differentiate that by doing u prime e to the u. So I know I'm going to write the derivative of the power, and I'm going to multiply it by the original function. What's the derivative of the power?
So the derivative of log is 1 over x over 2.
That's the derivative. Everything you do, there's a rule in the background that's telling you what to do. So it has to fit the rules like they're templates. So that's why it's very important that you know the rules. Why I ask them on the quizzes, because you do want to like see a rule when you're doing something. Like that's e to the log to the base 2 of x. No, it's an e to the u as far as I'm concerned. And the derivative is u prime e to the u. Okay, how do we do this one? Yeah? Were you stretching or? Yeah? Product rule. So you notice that this is actually one function, f, times another function, g. And so we know we want f prime times g plus f times g prime. And again, you don't have to write this out, but I want to show you what we're thinking when we're doing this. If you have to write it out, I mean, but it's not required. But yeah, I just know I'm going to take the derivative of the first guy, leave the second guy alone, plus leave the first guy, then differentiate the second guy. What's the derivative of the first guy?
8 2x plus 1 times 2x plus 2.
To the 7th power
To the 7th?
Oh yeah, 7 times 2x.
times 2.
Times 2, because that's 2x, the derivative is 2. Right, and so that here is your f prime. What did you just use to do?
Chain rule.
By chain rule.
And just explain it.
Right? Because we had a whole thing plugged inside and next to the 8 function. So there was an inside function here. Differentiate around it with the power rule. Then you have to multiply by the derivative inside. So the chain rule takes effect here. I am going to copy down the G plus,
F is just common.
no, leave F, differentiate the G.
And then 5 x squared plus 1 to the power 4 times 2x.
Right, so you have something to a fifth power. The power rule says you can bring this down and subtract 1 from the power. But the thing in the denominator, the base, is not just x, so you have to multiply it by the derivative. So you also use the chain rule there. So that is the first line. What is, how do we simplify this?
I have a
Yeah,
question.
yeah.
Okay, so you know how like the derivative of a constant is always 0, right? So there's
Yes.
like e as a constant. So how come in this case it's not like 0?
Because the power is not a constant. Right, so if you have just e, if you look at y equals e, that's literally a horizontal line passing through, 2.718 dot dot dot. Right, but if you have y equals e to the x, well, that's a different story. That's now an exponential function, right? So this is a function because of the x, right? The appearance of the x is what tells you that that's a problem. Now, if like in the quiz I had asked you, instead of an x, I put a 5, then yeah, that's a 0. That's now a constant, right? Log of 5 is a constant. Take one constant, raise to another constant, the whole thing is a constant. So that derivative would be 0. But it's not 0 because there's an x here. So this thing is actually changing values depending on the x. Okay? So yeah, it's very important that you examine to make sure that what's going on. What happens is that once you have an x in there somewhere, and your x is thought of as the variable, you probably shouldn't consider that thing a constant unless there's some other rule that tells you it's a constant, like the cosine squared of x plus sine squared x. You know from trig that, oh, that always equals a constant, so you can kind of replace that expression with 1 and then differentiate it. But otherwise, this doesn't really simplify to a constant. Yeah, that's a good question. It's important that you kind of look at things that deeply, actually. So that's a good question. You really want to understand how functions are put together, what the pieces are, how they react to each other, when something is a variable versus when something is a constant. It's a very important thing to do. Okay, let's actually simplify this in the sense of compress it. What would we do? As you will see in a bit, there are going to be times where it's very important for us to figure out where the derivative is actually 0. So there are going to be times where I'm going to get this expression, and I'm going to say equals 0, and I want to solve that equation. And we should know by now, when you see such a thing, your first instinct should be to factor the left side instead, which factor equal to 0. So knowing that that is kind of on the horizon, how would you actually go about doing that here? How do you factor this?
You take out,
Yeah, go.
you take out 2x plus 1 to the 7th power. And also,
Why?
because you see it's a common term on both the left.
Okay, so that's the first thing. When you want to factor, look for the common term. It's the first thing you always do. So we want to look for things that are factors in every term. There are 2 terms here. Notice that there's a 2x plus 1 in both terms. Anything else that's common? The what? The x squared plus 1 is a common term. Anything else common? 2 is a common term. Anything else? Okay, so once you identify the common terms, what do you do with them? You put them out in front, but what version of them do you put out in front? Huh? The lowest power. It's lowest power. So 2 appears in 2 locations. They're both to the power 1, so the lowest power is 1. I pull that out. 2 to the x plus 1, 2x plus 1 appears in 2 locations. Once it appears to the power 7, once it appears to the power 8, I will factor out the power 7. X squared plus 1 appears in 2 locations, once to the power 5, once to the power 4. 4 is the lowest power. I will factor that out. Then I write down what's left over on the inside. So I look in the first term for what I actually pulled out and what's left over. So the 8 I didn't pull out, so he stays. 2x plus 1 to the 7, I pulled that entire thing out. The 2, I pulled that entire thing out. Here I had 5 factors of x squared plus 1. I pulled out 4 of them, so there's actually 1 factor left. And of course, I had a big discussion about this in my other class the other day, but in Calc 1 I expect you to know that when you factor something out, how the other guys react inside is that you subtract the power that you factored out. So you pretty much think of this as the 5 minus the 4, which is a 1. When you factor out the 2x plus 1 to the 7th, you think of it as 7 minus a 7, which gives you the power 0, which makes that disappear. So it's obvious when we have integer powers, semi-obvious if they're all positive, but once the powers are fractions, students just forget this for some reason and write all sorts of crazy things here. Know the basic, simple ways to do things, really know the rules. Find common terms, pull out the lowest powers, doesn't matter if it's positive or negative, pull it out, and to figure out what the powers are of the things left inside, subtract the power that you pulled out. Okay, so now we have the plus from here. Now the 2x plus 1, I had 8 factors, I pulled out 7 factors, so I'm left over with 2x plus 1. The power would be 8 minus 7, which is 1. The 5, I left it alone. The x squared plus 1 to the 4th, I pulled that entire thing out. 4 minus 4 is going to be 0, which gives me 1. The 2 I pulled out, and then I'm left with the x. So that is the first step in factoring this. And I think we can continue. Plus 2 times 2x plus 1. So there's a set, get more space. I'll have to erase this. 2 times 2x plus 1 to the 7, x squared plus 1 to the 4th, times, this is going to be 8x squared plus 10x squared. Then I would have a 5x when this multiplies out. And then I would have a constant 8 when that multiplies out. So that would be the simplified version of this. So if I had to set this derivative equal to 0, I would first do this, and then I would set each factor equal to 0. So my x could either be -1/2 or no real solution for here. And here I would try the quadratic formula or something to see if it could actually factor. But that's what we would end up. Any questions here? The next one was very similar but with division. So let's actually work on that. So I didn't try new functions. I don't want you to actually focus. I actually want you to focus more on simplification here than the actual calculus because we did most of it. So I'll just take the same two guys, but instead of multiplying them, let's divide them. And what do we do here? Quotient rule. So I think of that as the bottom and the top.
You have to do the chain rule?
Yes, we're going to do the chain rule inside that. So we know that ultimately what we are going to want, we have the derivative of this. That's actually going to be bottom times derivative, top minus top times derivative, the bottom over the bottom squared. So that's what I'm going to write down. So I'm first going to differentiate the f, which we already did. This is 8 times 2x plus 1 to the 7 times 2 times the g minus, leave the f, times the derivative of the g all over the g squared. So what's x squared plus 1 to the 5th squared?
The power is 10.
The power is 10. Can you guess what common mistake I see all the time?
7.
7?
Like they would add instead of multiplying.
Oh, no. It's worse. At 25. I see 25 all the time. They square that and they decide to square the 5. You square something to a power, you just double the power. So that's a 10. Like I see 25s in this situation so often, it's unbelievable. Okay, so that is the first step, right? You square something, you double the power. You don't square the power. So now, again, oftentimes it's going to be very important for me to figure out when this is 0. So now we have to simplify this kind of guy. Now in the numerator, it's going to be very similar to what we did before. You're going to locate the common terms. You're going to pull out the lowest powers. You're going to write what you're left over with. The difference between this and the last problem is that there's just a negative sign here instead of a positive sign. So nothing really new to learn here. Let's just get through it. There's a common 2. There is a common 2x plus 1 raised to the 7th. There's a common x squared plus 1 raised to the 5th. And I will be left over with 8 times x squared plus 1 to the, this is the 4th, minus 2x plus 1 times 5x all over x squared plus 1 to the 10th. So what can we do here? First, now you'll notice that since we're multiplying, we can start canceling stuff. So that guy is actually going to cancel into this guy, and what's going to happen? We'd be left with a power 6 here. Because you subtract when you cancel. And so we would actually have 2 times 2x plus 1 to the 7th times. So now this would be 8x squared minus 10x squared. I'd have a minus 5x. And then I would have a plus 8. Back to the 6.
What happened to the 8x squared?
Oh, well, I multiplied out. This would be 8x squared plus 8. And over here, I would have minus 10x squared
Oh, yeah.
minus 5x. And then, yeah, those give me the minus 2x squared and then the minus 5x and then the 8. Have that. Okay, now let's look at one which would be very helpful on the quiz, actually. You could get around this, but there's a nicer way to do this. What if I had the ln on the first part? Okay, what are you going to do? How do you differentiate ln of something? What are you going to do here? Yeah?
I was going to do logarithms and do ln of 2x plus 1 to 8 minus ln of x squared plus 1.
Yeah. So again, this is another rule you can't get in trouble with because you don't want to have to do what we just did inside of another rule. One thing you can do is take advantage of the fact that there's an ln there, so you should simplify. In fact, this is probably a general recommendation, I would say. If you want to differentiate something, you should quickly look, can I just simplify it a little bit? I really need to jump into a derivative differentiation right away. In general, you kind of want to apply the simpler rules first, and just the laws of logarithms is a lot simpler than calculus. So you can just apply that first. So I wouldn't just jump straight into actually finding the derivative of that thing and dividing by that thing, having to simplify the top, then flipping the denominator and multiplying. It's just going to be a mess. However, what I can do is just realize that this is the same as the derivative of. Well, it would be ln of 2x plus 1 to the 8, but the log rule says I can bring that 8 down in front, minus ln of x squared plus 1 to the 5th, but again the log rule said I can bring that down in front. And I end up having to differentiate that, which is a lot easier. That is of course going to be equal to, constant factor rule says leave the 8 alone, differentiate the logarithm. At this point, I would use this rule because it's very easy to apply at this point. The derivative over the thing itself, minus 5 times the derivative over the thing itself. And so this really simplifies to 16 over 2x plus 1 minus 10x over x squared plus 1. Now, a lot of times, if I put this on a test or a quiz or something similar, the student's just going to run into the rule without really paying attention. And sometimes they're going to get it right, but with a lot of pain. So one thing you want to do is always want to look at the rule. Can you take advantage of the functions that are there and do something with that? So not everything is as complicated as it might seem at first glance. So if I had like e to the ln of the radical of x minus sin x plus 16x squared, you know, and I actually find the derivative of this, and that looks pretty scary. Well, it's actually not that scary, right? Because that goes away. Now you just have to differentiate that, right? So sometimes you don't want to have to like, if you didn't really notice to do that, what you'd end up doing is now you have to differentiate this and put it in front of this and then simplify that. And that's just harder than just seeing that, oh, the e and the ln, they just go away. And it's just power rule, that's going to give me a cosine and power rule over there. So that is an important lesson. On the quiz, there was a similar problem. Maybe I should look at that since we're here. X, for example, the derivative of ln of the radical of e to the x cubed over x plus 1 cubed. Now, if you look at that and just kind of run into it, and just decide, you know, I'm going to do u prime over u. Like, how would you find u prime for this? Well, you think of it as the half power. You're going to do the chain rule, bring the half down, get a negative half power. Then multiply by the derivative of the inside, which you're going to need a quotient rule with a product rule inside of it and a chain rule in the denominator. Like why? There's an ln here, right? The ln is going to tell me that the radical is going to be a half power, which I can bring down in front. And then I'm going to have ln of e to the x plus ln of x cubed minus ln of x plus 1 cubed. Ln of e to the x is just x, actually, so that's even easier. And the ln of x cubed, that's just 3 ln of x. And this guy is just 3 ln of x plus 1. So you could actually differentiate this a lot easier than you would think by just differentiating the x, differentiating that, and differentiating that. And that's the answer. Now, had you directly used this rule, it would be quite a nightmare to get to that answer, I can promise you that. So, simplifying, another tip there, probably also a general recommendation. If you can simplify using algebra prior to applying some sort of calculus rule, it is usually to your benefit to use it. You see ln's and exponentials and stuff, just take a quick glance. Can I actually do something with this before actually jumping into the calculus? Because chances are it'll make your life a lot easier. I'm not even going to do what this would look like if you had directly just used that rule in the beginning. But you can go home and try it for fun and compare. Compare which one you like more. Let's look at another one. How do we do this one? Chain rule. So what's the outside function here? The sine. So the derivative of that is going to be cosine of, leave the inside alone. Then I'm going to multiply by the derivative of the inside, which is cosine of? Now, there's another inside function. We need the chain rule inside the chain rule. And now I'm going to multiply by the derivative of that. So that's what that will give you. So you have 2x cosine of x squared times cosine of the sine of x squared. That was a double chain rule there. Hopefully you noticed that. This x cubed is not under the radical, it's small. Okay, now would we do this one?
one thing, like, can't you do u substitution for this? Like, you set, like, u equals radical e to like x plus 1.
Why?
I don't know, that's like how I did it, and then like I just plugged in u afterwards.
I mean, that's just doing the chain rule, but. So yes, you need the product rule. So this here is my f, that here is my g. So I'm going to do f prime times g plus f times g prime. Now to differentiate the f, how are we going to do that?
Chain rule?
Chain rule, because I have an inside function here. The outside function is the 1/2 power. So I would end up with 1/2 e to the radical x plus 1 to the minus 1/2 times the derivative of the inside. Now the derivative of the inside, the plus 1 is of course going to go away, so just focus on this. E to the radical x is what? The derivative of it. Well, you have the e to the radical x, and you multiply by the derivative of the power. The derivative of radical x? 1/2 radical x. X. Derivative of 1 is just 0, so that closes that, and then you leave the exponent here. Plus. Now you leave the first one, e to the radical x plus 1 times the derivative of that plus 3x squared. So here, this here is f prime with chain rule. Actually a double chain rule, and this here is g. Now this is f, and this is g prime. I mean, if you had to simplify this, this is the 1/2 power. How do you do that? Let's say I want to know where this is going to give me 0. How would I simplify that? Well, what do we do?
You said how, what did you just ask? How does it equal 0?
I want to simplify this.
You could just do factor. Can you just
Factor it, yeah. How would I factor this?
You see a common term of e to the radical x plus 1.
Okay, look for the common terms. This is step 1. So I know I'm going to write that to what power?
Negative half.
Negative 1/2. You always factor out the lowest power. Any other common terms?
X squared.
X's in both pieces. So I factor out the x, and I would factor out the square because that's the lowest power. What would I have left over? In fact, just to make this a little bit nicer, we could also factor out the half so I don't have to worry about the fractions inside. So what would happen now? If I factor out a half, that means I need a 2 here. But yeah, what's left over in the first term?
The 1 over radical x.
The 1/2 radical x, e to the radical x, times x, because I took out an x squared and there was an x cubed. Now, the 2's are going to cancel, and this x times that is going to give me a radical x e to the radical x, but let's worry about that later. What happens in the second part? The 3 is going to be there. What else? Yeah?
E to the radical x plus 1.
E to the radical x plus 1 is going to be there. To what power?
First.
The first power. Why?
Negative.
Because I pulled out a negative half, I'm going to subtract a negative half from a positive half. This gives me 1. So that's what we have left over with here, because we took out the x squared. So what I can do now is the 1/2 x squared, let's write this as x squared over 2 times e to the radical x plus 1 to the minus 1/2 times radical x e to the radical x plus 3e to the radical x plus 3. And that is our guess. So again, it looks different when I'm writing it on the board, but in terms of ideas and concepts, this is exactly the same like that example we did with the 2x plus 1 to the 8th and the x squared plus 1 to the 5th. Exactly the same thought process. There was no difference in thinking. And so some people, they see all these radicals and exponentials all over the place, it freaks them out and their brain shuts off. But if you really understand the basic rules, you can get through anything. So yeah, that's what that one would look like. And if I ever needed to set this derivative equal to 0, I'll just set each factor here equal to 0. Well, this one will go on the denominator. So that's what that one looks like. I think the other two aren't that bad. Let's just knock these out quickly. This is very similar to the sine of x squared example. So we're going to do the same thing, except the trig functions are just different. So just tell me what's the answer going to be here. Go. Secant squared. So that's what it would be. You can, just rearranging the terms for aesthetic reasons here. Minus 3x squared sine of x cubed secant squared cosine of x cubed. So that's how we do that. This one, quotient rule, neither the top nor the denominator is a constant, so I will just jump into the quotient rule. So it's going to be the bottom times the derivative of the top. That's going to be minus 1 over 2 radical x sine of radical x times, it's the bottom times the derivative of the top. That wasn't the other part, minus the top times the derivative of the bottom. That's the minus 1 over 2 radical x sine of radical x. over the bottom squared. So what's cosine of radical x squared? Huh? Is that cosine of x? No, right? It's cosine squared of radical x. The square on the cosine is not going to affect the radical. So, not much to do here actually. And that's the cosine squared of radical x. And I could factor out a minus 1/2, although it's not going to do me much good. Cosine of radical x plus radical x sine of radical x. Where that radical x comes from me taking this x multiplying, dividing by a radical x. And the plus comes from the multiplication of these two negatives. We kind of went pretty slow there, but I do want you to appreciate that sometimes you don't just rush into a calculation with some rule that you know, but the rules should always be at the forefront of your mind and they tell you what's allowed from what's not allowed. Probably try to apply algebra rules before you apply calculus rules in general, and you'll get through a lot that way. So it took a little bit longer than I expected, so I don't think it makes sense to start what I planned on starting. But maybe I'll just mention something else and then we'll go. The concept of a higher derivative. Just want to introduce this idea to you so you can start thinking about it, but we'll revisit later. What is the concept of higher derivatives? Now, as we've seen, differentiating a function f of x often, actually not always, even though in every example I've shown you this was the case, it's not true in general, but a lot of the time yields another function that we can differentiate again. So, for example, my function is x squared. What's the derivative? Well, it's 2x. But 2x is another function, and it turns out I can find the derivative of that. The derivative of 2x would be 2. And 2 is another function. It turns out I can find the derivative of that. The derivative of 2 is 0. And that's another function. What's the derivative of that? Well, 0. What's the derivative of that? Well, 0. Now it ends up being 0 forever. There are functions that we can actually differentiate repeatedly forever. These functions are very nice, and we can build things with them called power series, which is, you'll see in part 2, and those are very cool. They'll help us out in a lot of situations. Not all functions are like that. There are times when you can have a function where you differentiate it a few times and then you get some that you can't differentiate at all points again. But sometimes you can repeatedly differentiate something, and this yields what we call a higher derivative. So we can find a second derivative or third or fourth, potentially ad infinitum, right? And so we can find derivatives of derivatives of derivatives in a lot of times, and often these will have applications in and of themselves, which we'll discover some of these as we move on. But for now, let me tell you about probably the one that's most immediate. So let's talk about derivatives of a function f of x. Let's talk about the notations for this. That we can kind of split into two parts, actually. The Newton notation and the Leibniz notation. And let's look also at maybe an application. So we can have the 0th derivative. This is often important on a conceptual basis. It's often called f of x or f to the 0 of x. I'll talk about that notation in a little bit. Or Leibniz might call it y. A common interpretation for this is as a position function. It describes as a location. You tell me y equals f of x, you're telling me a coordinate on the xy plane. You can have what we call the first derivative. Prime notation is f prime of x. Leibniz notation is dy dx. This is often considered to be what? Velocity. This is an idea of speed that takes into account the direction in which you're moving. So now we can have the second derivative. This is called f double prime. Leibniz would be d squared y dx squared, because it's like you take a d dx off the d dx. The d's get squared and the dx's get squared. This is often interpreted as acceleration. You can find a third derivative. This would be f triple prime, so you keep adding the primes. D cubed y dx cubed. This is called a jerk. So if one of your smart friends calls you a third derivative, now you know what you're actually calling him. But you can continue this guy. Now what comes up is that eventually you get to derivatives that are so big that it's kind of ridiculous writing all these primes, like the 15th derivative. No one's going to be there counting 15 primes. And so you kind of get this notation here for Newton versus the Leibniz. He would call it f to the n of x. Now it's important that you notice that the power here is in parentheses. So this is not the same as f to the n of x. That's like taking a function, raising it to the n power. When you put a power in parentheses, what it means is you're taking that many derivatives. So the Leibniz would just be dny dx to the n. So if I wanted the 57th derivative, it's f raised to the parentheses 57, or in Leibniz notation, d to the 57 y over dx to the 57. And that's the nth derivative. Now these don't always have to all exist, but whenever they exist, this is how we call them. So this you can also call it f to the 1. This you can call it f to the parentheses 2. although we very rarely do that for the first three because you can just write the 3 notches. That would be called f to the 3, and so on and so forth. We'll look at some more applications next time. Well, not right away, but eventually we'll look at these specific applications here, as well as some other applications to what higher derivatives can give us. But it's just an idea. I want you to know that that's out there. Like, there is the concept of repeatedly taking derivatives, and there is a way that we can write that down to express that's what we're doing. We'll stop there. I will see you guys next week.